All right. Well, welcome again to the Center on Aging Colloquium series dedicated to methodology and, in particular, reproducible research. My name is Andrey Koval. I'm a postdoc researcher at the iLife Lifespan Lab at the University of Victoria and a member of IALSA research network. So we're ready to begin, so I'm going to kick into the presentation mode, and we'll go to slides. Today's slides are, as any preceding lectures, are available online. So I actually would like you to know how to get to these slides before we begin the lecture, so you can follow along if you choose. So in any Google or any other search engine, type in IALSA tutorials. That should take you to probably a GitHub page, and find the page that is called IALSA github.io/tutorials. And on this page, there will be a link to this event. You can also find this at the address noted here. So under this schedule that surveys the entire series, the latest edition is this, and this is what I clicked, and if you clicked it, this launches the presentation, so we'll begin from here. IALSA tutorial in the search engine, and find Center on Aging Colloquium series. So today's lecture is going to be on graph production. So to remind you about the context of the series, as you see from the schedule, the reproducible research concerns 6 lectures in the series, and in particular, I've numbered 4 of them that constitute, in my opinion, the core skill set that data scientists and modern modelers needs to have in order to engage in reproducible research. So we already talked about data manipulation, and today we're going to jump into graph production. So previously, I talked about this flow of data through a research process, right? We talked about this starting with question and arriving at an answer and going through several steps of data processes and analysis. And in particular, we looked at the process of making data tidy. We defined data as tidy and by how Hadley Wickham defines them as tidy. So specifically, we looked at this code called script, located in the scripts data DSLR. This is available on GitHub, so you can look at it either online or clone this repository and follow along and develop it at your own will. So the previous lecture was, in fact, an annotation to this script that took the raw files from NLSY97 study, extracted the content of the downloaded file, read a CSV file into R environment, cleaned, transformed, and then at the end exported as a RDS object, which is a native object, native data format to R. It saves it saves factor labels, unlike CSV, which does not. So the slides on data manipulation, or the previous lecture in the series, not Brian's, but before him, were in fact annotations over this live script, DSLR, that brings data to DSL stage every time it is sourced. And we've identified what those data stages were, at least in my understanding. So we're ready to move on. So we go ahead and source that. We take the fruits of our labor. We reference our past efforts in this data project, and we source and load this data object that we've completed previous time. str is a function in R that queries the structure of this object. So you can review that this has several variables, and you can see what type of variables those are. So let's take a closer look at the data and see it in tabular form. So here is the entire data set for a single individual with ID 1. We see that, well, there's 4 variables at the end that has ending capital F. And last time we've identified a place in our source file where we actually run code that attached these variables to our data set that stored labeled factors. So you can see variable sex here is stored as integer. This is how it came from the archive. However, we recoded it manually to be ordered factor, and it's called sexf. And other variables follow suit in the same manner. And it's going to be very convenient to have this ready set of variable, either the continuous, either the integer or categorical with label factors or not. So we want to have that at our disposal at every moment for modeling and graphing. So we're not going to be using every variable that we see here. So let's try to minimize our attention and focus it on some particular set of variables. So this is the set of variables that we'll be working today. ID, unique identifier of an individual, year of measurement in which the measurement took place. Attend is outcome measured on a scale from 1 to 8, measuring the frequency of church attendance. It was an outcome that I was interested substantively when I was working on this data set. So I inherited these examples. Excuse me. Attend F, which stores the labels for the values of attend. Sex F and race F, which also stores the categorical descriptive labels for these categorical variables. So this is what we have. This is what we arrived at from the last time. So next, let's take a look where we would like to be today. So this is our objective for today. We would like to create this graph, and we would like to understand how every aspect of this graph is being controlled by code, and how can we invoke that code to elicit a particular effect. So this is our end result. We're gonna start it slow. We're gonna start it simple, and I'm gonna narrate every step of the way so that you can understand how changes in the code result in the changes in the graph. So we start with very, very simple data set, which contains only 4 variables and 12 observations, right? This is a single data, the entire data set for the first individuals on these 4 variables, right? So these are all possible values of attend variable. And right now we're asking our question, how do we map these data to abstract dimensions? Because that's the purpose of statistical graphing, the graphics, the goal of that, right? So the most typical abstract dimensions is abscissa and ordinate, right? X and Y. Very typical. We don't have to limit ourselves by only those. We'll be able to use other abstract dimensions such as shape, color, transparency, and other exotic dimensions as well. So let's start. So we're preparing the canvas. We're starting from the very beginning. Here's our data. How do we take this data and map it to the statistical software? Well, there's a note or definition from Elegant Graphics for Data Analysis, a book with which Hadley Wickham introduced his ggplot 2. So he said that the data that you want to visualize in a set of aesthetic mapping describing how variables in data are mapped to aesthetic attributes that you can perceive. So that's mapping, right? We're taking the values in variables and trying to attribute them to the properties of aesthetic, something we can see, something we can perceive, from abstraction to some non-abstract and concrete dimensions. If you run this code, and again, just as previously, these slides are live annotations of the code, so you can look in the code that stands behind the slides and put it to work. So in other words, every code that you see is live and does what it claims it does. So if we were to run this code, so let's look at the side on the left side. Here in the statement, we define our DSM. And if you remember, DSM, we can go back to the model where we showed, DSM is a stage in our data development in which we're ready to start modeling. So it's most frequently it's a subset or some transformation of DSL, but that subset and transformation is very brief. So typically we want to have a record of how exactly we transform DSL to get to the DSM every time we run a graph. So a graph would almost would have to have a signature or a sort of a data genealogy, how we got to the data that went into the graph. So that's the purpose of DSM, so that we can take multiple disposable data sets from some stable data stage that we have identified and described as properties. So going back, yeah, so right here, we said, okay, so take this data set, filter, take only the observations for the ID, for the person with ID = 1, and select these four variables. How do we pass it to ggplot? All right, so this line reads the following: use function ggplot in package ggplot2. So the first name before the double colon is the name of the package. The second is the name of the function inside that package. Okay, so now then we open and we see two arguments. The first argument declares the data set on which this the function will operate, this ggplot function will operate. And the second argument is called an aesthetic, the mapping function, the function that pairs the concrete values of the variable with abstract dimension on the graph. So here we say, okay, we're working with two dimensions. One dimension is x, horizontal, another dimension is y, vertical. All right, we'll add other dimensions as well, such as color, for example, or transparency. We'll be able to do that. For right now, we're sticking with traditional Euclidean dimensionality. So if we run this graph, we will get an error. We will get an error that says no layers in plot. And that's a very indicative error because you've just created the canvas. You haven't created the command to for computer to leave any mark on this canvas. So you have to apply sort of a pen or some instrument. You have to start making strokes on this canvas. So the way you make strokes on a ggplot canvas is called geoms. And this is what we need to do. We need to add a new geom. And a geom is a geometrical object or geometrical object that represents what you actually see on the plot. It's points, lines, polygons, etc. And again, this is a definition how Hadley Wickham, the creator of ggplot, defined it. Okay. So let's make sure that we understand what's happening because this is fundamental. We have to see and make sure that we understand how these numbers become these dots. So we have an axis on axis, horizontal axis, we have year. So this is 2000, and at year 2000, the attend value was 1, correct. At 2001, so this must be the next one because we don't have the tick here for some reason. At 2001, it was the attend value was 6. So yes, it's 6. Then it's 2, and then it's all 1, 1, 1, 1. So it's clear here. There's no hidden anything in here. It's very transparent. Okay, so this is the very basic principle of how ggplot translates the numeric value into visible dimensions. Okay, so again, geoms are sort of like strokes, right? This is instruments that you can leave marks on the canvas. So points leave points. I guess what geom underscore line is going to leave? I bet you know what this is going to do. So if we change the geom, if we change the instrument, the mark that it leaves on the canvas is also going to change. So we don't have to be limited by number of geoms. We can have both of them represented at the same time. And in fact, there's a lot of geoms. And if you if you see a note here on the slide, you can press P, and that will bring up the note for this slide. So this particular note contains links to the references that list the geoms that are available to you. So you can see, well, there's a geom point that we've seen. There is a geom, where's geom line? Maybe it's not here because it's too basic. H line, AB line, which allows you to draw a line with a slope. There's a rug, there's a text, there's jitter, and so on. There's also an official documentation on ggplot that is an exhaustive source of geoms and options and settings for all ggplot knowledge. Okay, so this is how we define our canvas, and this is how we use the geoms, the instruments, to leave marks on the canvas. So let's see what else we can do. Well, you know, the background is before we do that, let me demonstrate you what this mapping function AES does. It pairs the values in the variable to the dimension on the graph. However, if you put this mapping statement, mapping function inside the ggplot statement in the canvas definition, that's going to be general setting for the entire graph, right? So all variables that you will be mapping on the graph would have those mapping. You would have X to whatever you specify in this statement, and Y to whatever you specify in this statement. However, there's a flexibility in this in these definitions. You can specify X in the general statement, and then you can specify Y mapping for each geom that you add to the plot. Right, so you can ideally you can put as many variables as you want, as long as you can differentiate and make patterns in them. So the next customizations that we can doing, apart from being very flexible for mapping variable values to abstract dimensions on the graph, ggplot is great for very flexible styling. So we can set up a theme that is a collection of attributes that all graphs that we produce are going to share. And then we're just going to apply these object that we call plot theme right here that is going to accumulate all those properties and will assign it to the graphs that we're building. So let me demonstrate what I'm talking about. So if we run the script, we've created a object called plot theme that contains all these settings. So then if we take and apply this or add this object to our graph, here's the difference that this statement will have. Here's the graph without the theme attached to it. Here's the graph with it. Now, if you go back and you start actually reading what goes into that theme, you'll recognize that, okay, so there's a axis title. There's increase in size in axis title. There's increase in size in axis title for X and Y. Text changes, and you can trace everything that happens in that file to the cosmetics, to how the graph looks on the page. So once again, there's a great variety of themes, and well, there's not that many themes, but there's a great variety of options you can implement within each theme, so that will give you enough variability to satisfy your publishing needs, at least internal publishing needs. And as you can scroll down, you can see what kind of things you can do with options described in here. Elements in these themes that help you manage the appearance of your graph and so on. It's a bottomless pit, and definitely a source of a lot of joy for me, because you never know what you're going to find and how it's going to make your graph look. So do browse these notes on your time to get to the good stuff of ggplotting. Okay, so we've talked about the appearance of the graph overall. Now let's attend a little more to the scales, to the axes, right? So as we see here, well, I don't know why there's 2000, 2004, 2008. I don't know why it's missing those. I guess it's automatic. So we would like to take control of that as well. So the next thing we'd like to do is to exercise the control over the X axis, right? So we add a element to our ggplot. It's called scale X continuous, which take various arguments. One of them is limits, right, which identifies what are the maximum and minimum values on the scale are going to be portrayed in the graph, right? So I took the extreme to demonstrate how it shows, but really we would like the limits that maybe 2000 to 2011, because that's the span of our values. So scales, and again, this is a definition from ggplot book. The scales map values in the data space to values in an aesthetic space, right? Those aesthetic mapping function, where it to be color or size or shape, right? So X is one of the aesthetic space. Okay. Next. Another function in this scale X continuous is called breaks, which identifies the tick marks where the labels or axis labels are going to be. So look at how the breaks are specified. So we're saying that the breaks are going to be equal to a vector that is a vector of integers from 2000 to 2011. So it's 12 integers from 2000 to 2011, and this is what we get, right? For every member of the sequence, of this sequence. Well, we can further customize this. So another way we can do, if we do not want every tick to be displayed, we have this option. We can, using comma instead of a semicolon, to identify which specific tick marks should be portrayed on the graph. So sometimes you do need that flexibility. Okay. So we've dealt with x-axis. Now we do the same thing to the y-axis, and we're going to do it at the same time so that we'll save some time. Right. Okay. So here's I'm adding the similar element to the to the plot that does similar thing to the y axis. So it limits the values to be from 0 to 1, and you can see how it changes it from default marking to the ones you specified. And also the breaks could be specified with a sequence function that reads as follows. So it says create the sequence that starts with 1 and continues until 8 and increases by the increment of 1. Right, so if you want to change, for instance, the origin or the interval in this function, you can modify it accordingly, and this is what you get. Right. Okay. Next, we would like to customize our titles on our axes, so you can further you can keep adding elements to this function scale x continuous. So add a comma and enter a string that to the corresponding axis. We get a year of observation on the horizontal and church attendance on the vertical. Okay, so the next we would like to add main title, and this could be accomplished by a geom GD title, which I like using. There's many ways how you can add annotation to the title, and it's basically what you remember, what you're comfortable with, what you know how to type in fast. So remembering words is just as important as knowing what to do. So your vocabulary is going to work for you if you know many ways to accomplish similar things. You're going to be a much more efficient programmer. So there's also, we could have accomplished the same thing. I just wanted to demonstrate identical. This is going to be identical plot. We're just going to use a different function to accomplish. So instead of putting it in the scale scale function, we put it in a separate function called labs that actually contains both title, the x-axis and y-axis titles. There's pros and cons using different functions, and you'll have to discover them as you work along and on your own. There's this great cheat sheet that I wanted to show you that I thought was pretty cool and was helpful to me, that gives reproducible examples of how to do, how to add a title, how to add a theme, how to customize theme, and so on and so on. There's plenty of examples that you'll probably find useful, or you'll probably find how to adapt to your own purposes. Okay, so let's move on. So next, this resource that I wanted to show, a lot of what I've found, a big stumbling block in getting to know and getting to work in ggplot is inability or infamiliarity with the anatomy of the plot. You just don't know what those things are called, so you don't know even how to phrase your question. So spending 30 minutes just browsing and trying to remember the names, just the names that are describing the elements of the plot, are going to be hugely helpful later on, because you'll remember, recognize, and it's always difficult to remember. Is it n row? Is it capital N or lower n? Is it n row or number of rows, or is it? There's many ways of spelling. So just putting it into your memory is always good. So there's this resource that does that and does a great job of describing this anatomy of a ggplot visually. Do browse it; is going to help you in the future. Okay, so now we've sort of did the basic. We've described how to take data for a single individual and map it onto visible axes, into visible dimensions. Well, we need more than one, right? So let's try to do it for two, right? Just like in mathematics, and two and three and more are going to be just an extension of that. So for this example, I've selected individuals with IDs 1 and 23. Now you notice this operator %, in %, and that means find the ID which belongs to one of those numbers, right? So if ID is either 1 or 23, keep that case, select that case. Okay, so we've selected two individuals, right? Each individual has 12 observations, so two individuals, we have 24 observations, and they're all are here. If you count, there's 24 dots, but the lines are doing something crazy. And that is because we have not set another dimension, and that dimension is a group dimension, right? So we want to identify that those 12 observations actually belong to the same group because they belong to the same individual. So we accomplish that by adding the mapping function to the geom line right here, if you focus. Right? So we're saying group these for when you're drawing lines, treat these observations that have the same ID as belonging to the same group. Okay, and that what allows ggplot to understand that you want it to draw trajectories for each individual. Okay, so if this is sort of understood, I wonder if what would happen. I mean, that's it. We just add more observations and we're done. So let's just go ahead and do it and just you know that. And that's what we get when we add a lot of observations. Right? So we're facing the overplotting issue. There's a lot of observations located on the same physical spot, and that's the problem because we do not know how many observations are in each point, and the lines that are supposedly should tell us how many people transition from one category to another are all overlapped too. So we've graphed it, but it's useless. So we got to do something about it. So one of the way how we can address the overplotting issue is called jittering, right? And jittering is introduction of random noise to your data, right? It's randomly seeded, so you cannot control it. If you want to control it, I believe you have to create your own data or run it from a seed. I don't know for sure. But every time you rerun the plot with a jitter function, those random elements is going to be recreated randomly. Okay, so what we can do is to add this random noise. So let's add this random noise to the lines that describe the trajectory. So let's look at the code, first of all, and identify where the change happened. So everything else on the top stays the same, but this line where it defines geom line begins to include the line with position equal position jitter W and H. So W is width, H is height, right? So we're saying identify the square 0.3 by 0.3 and randomly disperse the points within that within that square, right? And I'm sure you can look into the randomization mechanism on your own. I didn't delve that deep, but it's scholastic. It's stochastic. It's good for us. So let's look and try to notice the difference in the lines that it made, right? So we're beginning to perceive some patterns. Look at that. We have a lot of lines right here, and that corresponds to category 1. And category 1 is, no, I don't attend church at all. So we see a big proportion of population who just don't go to church and don't go up, right? And we also see a bunch of lines right here, right? And that's people who sort of were going to church here, but then just drop suddenly over here in these time points. And that's pretty much all the patterns that I can make right here, because it's so messy. I mean, I cannot make out anything. So apparently we're not done. We got to do something else to pretty this up so we can see some patterns. So if this jittering did change our lines, let's see how we can jitter our dots. So when we jitter our dots, right, so let's look, we see right here we have the line that makes our dots jitter, right? We get, well, I don't know, it gets messier, right, because you get started competing with the line, so it's get a little bit difficult to see what's going on. So another issue, another way we can address the overplotting is start using third dimension, and that's color. So that's what the next thing we're going to do. Oops. Yeah. So let's look at where the code lives. So we're adding a section right here that adds color to the geom line. So now the geom lines, this tool that we're leaving marks with, are leaving marks with color fire brick. Well, what's the fire brick? Well, R has its own color definition, and I found this very helpful. Here's the colors, and here's the names for those colors, right? So you can find the color that you like and sort of remember it, and type this instead of the 6 or RGB coordinates. So this is nice for like quick graphs. However, when you become like really precise and you need to figure out the color very precisely, I recommend using colored.org, and it goes to org. And it doesn't go. And colored brood, that should go. And yeah. Okay. So you can select the scale that you would like to work with, sequential or divergent or qualitative. And here's the palettes that are optimized for a number of divergent categories, or there's options to make them colorblind safe, or select from the palettes that are colorblind safe, photoable, and other options. So these are really I use them a lot because you can merely select it, and now these are coordinates you can input into R. Or if you select hexagonal, this is how you can identify and pass this color, this particular shade, to R to use in the graphs. Okay, so those two resources are fantastic for that. Okay, so we've added color. We made our lines red. Well, that cleared up a little bit. Okay, so we can now, it's very easy to tell the dots from lines. Let's do the same thing to the dots so we can sort of control the color completely. And now we've made our dots blue and our lines red. And here's the line that is responsible for that. So right here, we're adding 3 values or 3 arguments to this geom point function. Shape equal 21, color equal NA, and fill equal blue 4. Well, hold on a second. Color and fill, I did the same thing. Well, fill, because of this function shape, let's see what that shape does. Shape is actually, there's two resources which you can consult that list the numbered shapes that you can use for your plot. So if you want, the one I used is 21, right here. This shape is great because it has two parameters that go into it: the inside color and the color of the surrounding circle, right? So you can even if you like transparent, you can make the color transparent, but the circle around to stay solid, so you can identify it a little bit better. So, and you can choose and see what shape works for you best. But because I've identified shape here as 21, I specify what color I would like to be for the circle and for the filling of that circle. Okay, so we've explored jittering as one way to overcome overplotting. We've identified color as another way to overcome overplotting. So the next thing I would like to demonstrate is transparency, or alpha level, right? And that we say, okay, the how transparent the color that you painted with, that's going to be tied to the data, right? To however many lines pass through that path. So that is convenient, because now if we make it if we make the dots transparent, we can sort of see if the blue is more intense, it corresponds to the higher density of those dots, right? So that gives us a better idea of what's happening in terms of distribution of frequency in here. And let's see how it's accomplished in code, right? So we add a statement called alpha, both to geom line function and geom point function. So both of those are going to be 0.3 transparent, right? Alpha has values from 0 to 1, and the percentage, right? How much transparency or translucency that has. Okay. So this is really gets to the sort of artsy part, because I cannot tell you what should alpha, what should jitter be, what should. You have to look at your own data. So this, we're selecting 300 individuals for this, or at least no more than 300 individuals. If that was 6,000 individuals, it would be a completely different thing. We might not even see anything in here. We might need to either to make it very, very transparent so that we can barely make the patterns in the shading, or maybe we need some other expressive language to accommodate that amount of observations. But for 300 people, it works here, so we're happy for right now. If our input changes, we would have to address it somehow, either on data level or on the graph level. So let's see if we can play around with some of these values of jitter and size and transparency to get the story a little bit clearer. So the first thing that I sort of played around and saw, well, there's maybe two ways how to approach this. Well, one way is look at the alpha size. So alpha is small for the thin line, so we make lines thin, and alpha decreases for the dots as well. So we make dots fainter, and we make size a little larger than average. So the default line size about 0.1, 0.5, 1.8, I don't remember. But 2.2 is a little bit larger than the default, right? So we make dots fainter and larger, and that's the effect, right? So it's you cannot see the dots clearer, but you get the bigger picture a little better. Well, maybe we can try a different approach, and that to make dots smaller but actually increase or reduce their transparency, make them more vivid, right? And that will result in something like this. Which one is better? This one or that one? I don't know. It depends on what kind of questions you're asking and what sort of thing you're looking for in your data. It might be that this speaks to you, it might be that the previous speaks to you. So usually you go through hundreds of graphs and you keep only few that actually tell the story, and that's okay. Okay, so we're very close to the end. Well, we've done, we battled over plotting. We've taken care of our axes. We've taken care of our labels. So now, what stops us from that original goal is to plot this very graph that we've actually described here in this code, to plot it for different groups, and that is accomplished by another geom or element in ggplot called facet grid, which very easy to understand, right? It sorts distributes sex F across race F categories. If you wanted to distribute only across one category, you would put a dot instead of one of the variables, and you would get either vertical or horizontal distribution. So when we do this, here's what we get. We actually, there's more than 3 categories of race, right? So there's black as identified in NLSY. There's black, there's Hispanic, there's non-black, non-Hispanic, white, or there's mixed, non-Hispanic, as identified by NLSY 7. Well, there's not that many individuals in the 3rd category for us to keep this facet. We don't want these individuals. There's a few. We cannot enter them in any model. They might be outliers. We want them out. We want to exclude a level of a factor. How do we do this? Well, you cannot really, you can do it in ggplot, but it's much easier done if you address it with the data. Remember that DSM stage, this is where it kicks in, right? We modify slightly the definition of the DSM, the genealogy of DSM in relation to DSL, and because the DSL is stable stage, every time we reference it with a different genealogy call, we got our clear and precise definition of our data. So let's see how it's done, how it's handled on the data level. So see the first line right here. So pay attention what happens here as I switch between the views. It adds this second condition to the filter statement, right? So the filter statement in the DSL, in the dplyr package basically says get this data set, DSL, and keep only the observations that match the following criteria. And the criteria so far, in this case, the criterion was a single one. Keep only those observations whose ID, whose value on ID variable is less than 300, right? So we said keep individuals whose ID is no higher than 300. Well, here we add the second condition, right? So this is, and in addition to that, also keep those individuals or those observations whose value on race F variable is not exclamation mark equal sign, is not mixed or non-Hispanic. All right, so we say exclude that and repeat everything you've done before. Just address, right, we do not change a single letter in the definition of our graph. Graph stays the same. We slightly change the data. We have the graph that we want. But there's a problem, right? We cannot read this anymore. There's again overplotting. If we're going to make the labels very small so them fit, we won't be able to read them too. So what do? Again, we can tweak the data a little bit, again, the DSM, so that we don't have to, we can keep the code for the graph the same. What do? Well, we create a new variable. We create a variable that is basically a centered variable of year, right? So we say, instead of having 2000, 2001, 2000, we'll just say 1, 0, 1, 2, and we'll identify this variable as years since 2000, right? All the information is preserved. We just made our information communication more efficient. And that allowed us to see every axis label on this graph, right? So we're getting very close. This is has these alpha and psi settings, and as I was playing around finishing up with this graph, I felt that, you know, these give us a little bit better chance at guessing what the patterns is. This is a subjective call. You can prove me wrong by showing what you got. So this is the graph that I started our lecture with. It may not be the best graph, but it's a graph that you can build in 30 minutes, and it's a very efficient and potentially elucidating graph. Like, it can tell you something about the data that you didn't know before. So let's see what it tells us. Well, once again, we see a clear pattern of a lot of people staying on this level of 1. They're staying home. They don't go to church. There's a lot of transition right here, right? So from higher attendance category into lower attendance category, but it seems that they are prevalent among whites, not as much as in blacks, really, because these are clear here. But we're not sure whether that is because there are just fewer people or not, right? So we think we see something in the graph, but then immediately we think of other threats to validity that can endanger the conclusions that the graphs try to entice us to. So as we think of these threats to validity, we start developing new ideas for, well, what does the graph or the model in the graph needs to incorporate to address those threats to validity that endanger the validity of our conclusions. And that's what we're going to talk about next time. What can we do beyond describing the observed data? How we can transform it? How can we re-express it using mathematical formulas so that the patterns become more apparent, so that the patterns become easier to detect? If there is effect, yeah, the graph can probably detect it if there's a big effect. But if there's a minute influence, if there's a small and faint influence of some factor, you need mathematics. You need some aids to be able to detect that. And that's what modeling and graphical, statistical graphic is aimed to do. So next time, we're going to pick up from here, and we're going to develop these graphs into statistical models and see how graphical instruments of ggplot and RStudio can help us understand, touch, and play with statistical models. So this is all the material I have for right now. If you have any questions or comments, please feel free to forward them to Anne Greenwood or Vincenza Grupposo, and you see their emails right now. They're standing by to take your questions. And so with that, thank you very much for your attention.
Thank you very much, Andrey, and then lots of resources for people, and I can't say enough about all the support you're providing people for these for this series and for their follow-up work. So thank you very much once again. There was a question earlier on. One of the individuals who came in today was wondering about just practicing with R software and any suggestions you might provide in terms of places they might go for resources to practice.
Yes, so I would highly recommend getting a book called R Cookbook by Winston Chang. It's structured as a cookbook, so it gives you a list of problems or a list of tasks you can accomplish while graphing. So what I would do, I would just take and try to recreate every example in that book. It's fairly easy. It's fairly straightforward, and you learn a lot, and you get your arsenal of and your vocabulary in ggplot expands very well when you do that. Other than that, there's a danger of having too many resources, and you just don't know where to go. So I would select 2 or 3 or 4, and I know it. I don't want to be responsible for that, but for you not, settling on only a few. But at first time, I would keep it down to just a few resources. You don't overwhelm yourself. So a quick R is a great resource. The ggplot official documentation is another great resource. Most of I've put pretty much all the links that I go to regularly in this presentation. So all the pop-up notes will take you places that I go and visit regularly. So those are the great places to start. And also don't overlook Stack Overflow and Google Groups. The people who develop these software are very active in development, so they constantly bring new products, and they constantly engage in conversation with their users, with their clientele. So I learn a lot from conversing with them and seeing what they're doing. So that's another great resource.
Thank you very much. Anyone else have a question?
This might be too detailed, but it occurred to me when you were saying, showing the slide at the end with the facets, and you had black, Hispanic, and non-black, non-Hispanic. Presumably, it would be possible to deal with the frequency issue by selecting random subsamples of the same size from each of those groups when you're at the DSM or creating the DSM stage.
Yeah, that's one. That's a data side how you can approach it. And frequently we would balance between how can we solve it from data side, how can we solve it from graph side, how can we solve it from model side, and so forth. So I think that's definitely is a solution. Thank you.
Thank you, everyone. Once again, if there's any further questions from the online audience, please feel free to email them in. We can always deal with them after the presentation if you have a burning question that we haven't addressed for this series. And once again, thank you for everyone who's attended, and please check your schedule for the next session. Andrey will be here next Tuesday, same time, same station. Oh, 2 weeks from now, sorry. We have November the 11th, that's right, as a holiday. And so we won't be here, but the following week we'll be back. Anything else we should add?
For those who've missed earlier lectures, the next 2 weeks might be a great time to sort of catch up on what you've missed and let others know that they can do that. And so by the time November 18 comes around, you'll be all caught up and ready for the next lecture.
So spend next Tuesday doing it.
Absolutely. Absolutely.
Well, you can go and recreate and try to reproduce everything that I've shown.
Yeah, you'll be a pro.
Data points on a person, could you then compute the mean for that person and then fit a best plot, fit a line to that person and then look at the variance of the person over time from their own mean and then exclude cases where you have too much variation because it looks like it's sort of random.
Yeah, you can do that. Next time I'll be doing random coefficient modeling that you can subset data based on the values of that individual means and variations if you want, and look at that. Again, you're going to be losing you're going to be losing the sort of quality of your conclusions, right? It's sort of is going to be more exploratory rather than confirmatory mode, because you cannot subset get a sample that fits your needs and then say, "Ha, I discovered some patterns that in this sample." But it will allow you to maybe tell a story. It's going to be biased, but you say there's a story to be told. That specific people, we cannot generalize it maybe on the sample, but there's a story to be told if we limit to that. And that's one of the things that we're going to be doing next time.
Okay.
All right, thank you. If there's no further questions, then we'll see you in 2 weeks' time. Thanks again for tuning in.
Thanks. Bye-bye.